So I already did a lecture for exponential functions before spring break, so this one here is just a couple more examples. Here's one, data for the exponential decay of a radioactive isotope. By the way, when you look at this, this will look really similar to the take-home test that you're going to take. So supplied, so the exponential decay of radioactive decay, the data are supplied with activity A measured in becquerel for each elapsed time in days. Graph these data and use an exponential regression. So here's the time in days, here's the activity in becquerel, and these are the things we have to do. Among them is to write down an equation of this form. So activity is the original activity times e to the negative lambda t, and then we have to answer these kinds of questions here. So let's do that. I already started doing that in Desmos. These are the same data that you just saw, and here they are. They graph nicely. If you do this here, that's of course fine when you move around or zoom in or zoom out. But if you want to have it back to the original one, click that little plus symbol here, zoom fit, right next to the table, and there it is. All right. So find an algebraic model. I'm going to use these here, y1, x1, because that's what Desmos gives me. So it's going to be y1, I just typed it the way it is, then proportional, not equal, but proportional to the activity, original activity level. I call it A0. Actually, that's not going to work. Let's call it A1, times e to the, and it recognizes that the little e here is actually the number e, which is 2.7181 and so on. And then I'll hit the little caret symbol above the 6, so that gets me the exponent. I'm going to put a negative there. At least I try. There we go, negative. And then it doesn't take lambda, so I'm just going to use k instead. And then instead of t, of course, I'm going to use x1, just like Desmos suggested, because there's the data. Okay, here's actually the equation. So there it is. The A1, that's the original level, is activity, which is 207. We can see that right here. This is the first data point we have, which is at 161. But when we do that regression curve here, which looks really nice, by the way, we come up with that at 0 days, the activity level would have been about 205. That's the way the graph looks like. And here, of course, it says around at 207. And the decay constant is the 0.257. Of course, there's also a negative in the front, which says that this exponential is going down, so there's decay. The fit is actually really good. All right, let's plug in these answers. So the original activity level should be a little more than 200. It is. Exponential decay constant lambda should be about 0.25, which it is. Write down the original activity A0 and the exponential decay constant lambda. So this one is then the 207 rounded, and this will be becquerel, BQ, and the exponential decay constant lambda. So that one is the 0.257 rounded, and then write down the equation. We already did that. So that's kind of give away how good is the fit. We decided that putting the exponential on the decay here is really good. Looks like a really good fit, almost perfect data. That's kind of expected in radioactivity because the decay really does follow a particular exponential equation. Based on the graph and or the data, estimate the isotope's half-life. So let's go back for that. So here we have a little bit more than 200 to begin with, which means we're going to look at a little bit more than 100, and that's close to 3 full days. So almost 3 days, that's what we would say here. And then use this formula here for the half-life to determine it actually, and it's not in hours, it's in days. So when I do that, I compute natural log of 2 divided by the 0.257, and I come up with 2.697 days. Oh, which should be a little less than 3 days. There you go. Whoopsie. At this website, this one down here, find the isotope. So we're gonna look at that. It should be toward, well, I don't know about that, toward the end of the second row. Yeah, that actually should be here. It should be kind of in the middle. Of the periodic table, which is not what we're going to look at, a periodic table, but if you look at one, you will notice that it's kind of in the middle once we look it up. So we're going to look at 2.697 days. Actually, here is a periodic table. We're kind of in the middle here. I had to fix that because, and there's a phone call. So I'm going to click on, I believe it was this one here. So here we have 2.695 days right there. And that would be gold 198. That would be the isotope. Kind of cool. So I go here. It has a half-life. Well, I just determined that. And it decays into 198 mercury, which is, by the way, a stable isotope of mercury. And then here are some applications that we can see. Nuclear medicine, radioactive tracing, I guess nuclear weapons. So how does the isotope, oh, find the isotope, and that one here would be gold 198. How does the isotope decay? Decays by electron emission. I actually just looked it up. Let's see, it should have been here, right there. Beta minus means electron emission. If it says beta plus, it would positron. What is the isotope used for? And what I'd say a moment ago, nuclear medicine, radioactive tracing. All right, that was one of the examples I wanted to do here for exponential functions, in this case the decay, which has the negative in the exponent to show that it's going down. As unfortunate and as sad as it is, the exponential equation can, of course, also be used to describe things like the coronavirus. And I use Italy here. I got the data from this website, Worldometer. And when I click on Italy, we can see here's the exponential curve. That's where I get the data from, and unfortunately it just increases and increases and increases. So what I'm going to do here is I'm going to show that the exponential growth equation should be of this form here. There is a certain initial population. There's a reason why this one says negative 800 about, and we'll see in a moment. The exponential growth constant k should be about, and this is a little bit off the screen, so 0.15. And then write down the initial population, exponential growth, write down the equation, how good is the fit, and based on the graph, estimate the doubling time of infections. I already gave the answer away here, about 5 days. Use this equation to determine the doubling time in days, which again, when we do this carefully, we come up with 4.4 days. Comment on both exponential curve and the linear regression. And I'm not going to answer these questions here, they're just too sensitive. Is Italy able to control the virus? Well, we certainly hope so. Will it stop? Well, we certainly hope so. So I guess to a certain extent I did answer them. Okay, so let's look at the data. So here I have transferred them in here. The dates do not graph, but here are the cases. And the reason why I have 25 days over here, and let me actually push that further in. There we go. 25 days over here is because day 1 is actually when it really started in China. So this is day 25, which is mid-February, and then so on. And so I have these 56 data. So I'm going to graph these. Click on this one here, and there are the data, but they don't show up in the window. So I'm going to click this little symbol here, and there they are, except they're off the screen. So there we go. And then I will put in the exponential here. So Z4, I'm not going to type the as an equation, but Z4 is proportional to, it's always shifts us up here when I do something. There we go. Maybe that's a little bit better. So Z4 is proportional to A4, and this would be the initial amount of infections times e to the, and then a factor k, and then the time variable x4, and then technically that should be it, but we're going to put in y-intercept here, and I'm going to change the color of this curve here. And then what I do is right behind it, I'm actually going to cut off this line here. So I'm going to say x4 is less than 64 days. It's supposed to read x4. There we go. And close the parentheses. There we go. All right. So here is, this is the initial one, 5. As I said, negative 800. That's because there were virtually none back here, and I already started with 25 days here, so there was this fake negative 800 there. The growth constant here in the exponent is 0.156, as I said earlier, and we can see that this really increases rapidly, unfortunately, of course. And here I cut it off here. If we compare this with China, and I'm going to do that in a later recording. I think this is China here. We can see this one here and China's curve, which I believe I put here. There we go. I will do China later because this is a logistic curve, and I'm going to see it. Just this one here. There we go. See it a little better. I don't know why there's such a big gap, but I'll talk about that later. Yeah, the unfortunate thing here is that Italy appears to actually catch up to China as far as infections are going, and I hope that they're going to get it under control soon. So the initial population is at about negative 800 or negative 796 is what it said. And again, it's only because of the way the data came out. The exponential growth constant is 0.156, and of course it's positive because it's growing. Write down the equation. So n of t number equals the initial number 700, negative 700, no, hold on, 5.2, and actually that's not true, it's actually 5.22, the other one was the y-intercept, which was still negative 800, I'll write that down in a moment, times e to the, and that one is 0.156 times time, and then we have this strange y-intercept of minus 800. How good is the fit? Well, the fit is unfortunately very good. Based on a graph, estimate the doubling time of infection, so I'm going to look at that again. So here we go. Let's see, I'm going to zoom in. So here, for example, we have 10,000 after 49 days, and we have 29,000 after 53 days. So that is approximately 4 days. Whoops. Yep, about 4 days looking at the graph. calculating that on the side, so natural log divided by the exponential growth constant 0.156 comes out to 4.4 days. You can do it on a calculator. And again, we hope that it will soon actually level out and not continue like this one here, but level out like China is currently doing. This is March 18, 2020. And South Korea started doing that too. Italy is among the many countries where it's still going up exponentially.